Chapter 7 and Chapter 8 together are the parts of your text that introduce energy as an idea in physics. Energy was not uh, recognized as such by Newton in the Principia Mathematica. It was an idea that emerged out of study and application of physics, a few centuries after. Um, we're going to discuss energy first in terms of building up what's called the work energy theorem, which is a general statement about how energy can be transferred by forces doing this action called work. And then in the next chapter, chapter 8, we'll introduce the idea of potential energy, which is energy that can be stored by the work done by particular kinds of forces, conservative forces. So our first step is to just learn about energy and then the work energy theorem. And then we'll see that there are certain forces that have a certain symmetry, giving rise to a particularly easy way of dealing with the work done by those kinds of forces. In the background picture, I picked one of the nighttime space shuttle launches from Florida. It's something I would like keep in the back of my mind of the exchange of energy. So we're going to see there's a tremendous amount of energy that is being released by the space shuttle, ultimately to raise it from ground level through the gravitational field of Earth up until it's in a comfortable orbit, a few hundred miles up in the sky above the surface of the Earth. All right, at first, we're just talk about energy in very broad terms. So, energy is like mass or charge. It is a property that some object can have. Okay, energy can be transformed or from one form to another, and it can be transferred from one object to another. The transferal of energy is done by the process of doing work. So forces can do work to change the energy of an object. Out of the conservation laws that we are going to utilize in physics at this level, energy is probably the single most useful statement. Conservation of energy can make what would be very difficult analysis of motion into something that's much, much simpler. In the writing of your textbook, conservation of energy is an absolute statement. That is not exactly true. It's perfectly fine for a class at this level, but conservation of energy becomes very very unclear in the context of general relativity. And so in cases where general relativity is dominant, for example, in cosmology, then conservation of energy is not going to hold, or at least not in a way that you would pleasingly think of it in terms of I have some calorimeter and I burn up some substance and I see how much that changes the temperature of water, and I can tell from how much the temperature of the water raised, how much energy is released in that chemical reaction. We have a great deal of confidence in conservation of energy, like on a local scale. What's difficult is defining energy and conservation of energy in some global sense in a curved space-time, but that's beyond the scope of this class. It's sort of like a little physics enrichment there, that sweeping terms about conservation of energy can be a little misleading. All right, the first kind of energy that we're going to meet is called kinetic energy, and that is energy that is in the motion of an object. And so kinetic energy in our notation is going to be a capital K, and observe that it is the quantity a half times the mass of an object times its speed squared. That is the kinetic energy. Energy is used enough that we have a compound unit made out of basic units to express energy. So in our MKS system, the mass gives us a kilogram, and then speed squared is going to give us meter squared per second squared. And that combination comes up enough that it's useful to have something shorter. And we call that a joule after an English physicist. And then the short version of that is a capital J. So the unit of energy we'll use is a joule, and 1 joule is a kilogram meter squared per second squared.